Okay, there we go. Yeah, so hello and welcome. This is a very special talk to me because that means I'm so out of organizing this conference that they're letting give me talks. So just as an illustration there. So who am I? I'm Florian. You can find me on Twitter and on GitHub. I own two companies, one that has nothing to do with programming languages and the other one that does just Rust. I do program Rust since 2013. I do train it since 2015. And since then, I am a team member. I've also formed a couple of community things. I'm part of the community team. I founded this conference. I founded another conference based on embedded subjects. So I've been active. Today, I'm going to present the async-RS, async-std project, which is, we thought about the name for a while, and we came up with 20 names until we figured out, yeah, we're going to call it async-std because that's what it is. It is a port of the Rust standard library into the async world. It takes the whole interface of libstd, everything that does I/O or anything that might be thread blocking, then puts it on top of an executor, and the rest of the interface is based on the futures RS library, which is the abstract interface to working with futures. The futures trait that was stabilized within Rust is a very, very minimal one to allow libraries on top of it to write extensions to it. It really has the bare minimum interface of this is what a future is, and all the operations that you can do on top of them are provided by the futures RS library. Async-std is not new. It's the summary of 3 years of experience. The people that have kicked it off were, first of all, Stepan Glavina, who is also known as the maintainer of Crossbeam and used to work on Tokyo, and Joshua Wyatt, who works in Python and Surf, and me joining early. It's now developed by a global team, so it is a community project with a lot of the development nowadays being done by community contributors. So why are we building async-std? First of all, stability. We believe that the Rust async ecosystem has been in flux for far too long, and we don't want to iterate further. We want to collect the knowledge of the last 3 years and implement them in a library and give it to you in a stable fashion that you can rely on. Ergonomics. It should be easy and consistent to be used, and we figured out that the standard library interfaces aren't actually bad. So there has a lot of work has already been done around ergonomics, so we have adopted them instead of coming up with our own again. So again, not doing research. Should be accessible. It comes with a book and full API docs. So we have extensive API documentation. It fully integrates with the wider Rust ecosystem, mostly with futures RS. So it uses futures RS as its base interface. And speed. Speed should come out of the box, so all this shouldn't be slow. And we believe it's the best library to get started with async await. And I want to give a personal motivation to the first point. As a trainer, I found it quite interesting that over the last 2 years, I have seen more and more people not be interested in async Rust training, particularly to the point where last year people have said, can you just skip the async part? We're not going to use this for the next 3 years. This is too much in flux. So this is the state we're in, just to be clear. It has a couple of additional properties. It has a very small dependency tree. It is not overly generic, which means it compiles fast and does not expose you to an end application, or does not contribute to an end application that compiles from it. Let's talk about async. So this is a synchronous function. It takes a path, returns I/O results, it reads a file, and by opening it and then reading it into a buffer through the read trait, and we provide the capability of doing this, basically adding async-std in front of it. The only difference is that you need to manually add the prelude, because the compiler doesn't do that for us. And then you put async on front of the function, and every operation here becomes an awaitable future operation. So file open will notify you once it's done, and then you can continue. And the same goes for reading. Yeah, and yesterday someone, particularly Pascal, met me here and said, well, yeah, we used it internally, and that really works that way. We took our sync code, put async on top of every standard import, and it worked. And this is intentional, because async-std exports all types necessary for async programming, including some re-exports of standard library type. So if we're talking about I/O result here, that's the same I/O result as the standard library has. And why are we doing this? The standard library has the habit of, at some points, actually being subtly blocking. For example, standard path path has blocking function, particular exists or metadata and all of these kinds of functions. So if ever there's a type within async-std that is not in that is also in std, you should use the async. But talking more about what async functions represent. So this is a manual desugaring of what the async keyword does. It does a little more. For example, it activates the compiler mode in which you are allowed to use await within a function block. But the most important thing is it turns the return type of a function into impl future item and the result that we have stated there. That is, that also gives an interesting insight in what those functions do. They generate futures. They don't actually do work. We'll come back to what that means in a second. But what does the await mean? The await means at all of these points, there is an operation where this task has to wait for something to complete. So it will indicate actively, I have to wait, register interest in a certain event. In the first case, I want to open a file. Please tell me when you're done. And this is what await. The active indication that you're waiting. It's also called completion-based. So await is the moment where you wait for something. If we call this function, we get a nice compiler warning, which is futures do nothing unless you await and call them. That's what I mean by async functions are generating futures. So the return type of this is a future that will open this file. So it kind of moves the thinking in the future. That's where the name comes from. You're asking for please set up my program so that it can now open this file and tell me when you're done. And what do you need to run them? Futures are run using a task. And that one's important. And there's multiple ways to get to a task. Those mostly differentiate in blocking, non-blocking, blocking in the background. I come to the exact semantics in a second. The important thing is multiple futures can run in the same task currently. Tasks themselves may run in parallel. This is depending on the execution strategy. I'll come back to that in a couple of slides. As a differentiation for this talk, this is a really, really rough definition, but concurrent means multiple processes run in a group, yielding to each other when they need to wait, usually called cooperative scheduling. So any of those operations will go until they need to wait for something again and then actively indicate, I'm waiting, someone else can run. While parallel means multiple of these things run next to each other, usually on multiple threads across multiple. And when we talk about blocking, in this case, blocking, sadly, as many IT terms is not sharply defined. For this case, for this presentation, when I say something blocks, it is blocking the thread that's currently on, which means if you have additional concurrent tasks on this thread, they will be blocked as well. And that is a huge problem, and this is something to avoid. And this is why we choose how to run our futures act. So this is the task block on interface in async-std. You will pretty often see that in examples for the reason, that you need to block the main thread, as the same goes for any kind of example that does threading. You need to block the main thread to make sure that your program doesn't exit while something runs in the background. So all examples pretty often use task block on, because the definition of task block on is it blocks the thread you're currently on and instead runs the task that you are passing. So in this case, for example, reading the file. The nice thing about block on is it actually gives you the results back like if you had called a normal function. Because you can do that, you're waiting, you're completely blocking the thread until it's done, and then you can collect the result and immediately put it into a variable. The second interface is spawn. Spawn runs a background task concurrently and waits for its completion. Doesn't wait for its completion. It gives you a join handle back and block on. You can then call block on the join handle, blocking the main thread. The semantics here are spawn spawns the future that does the operation, and it gives you a join handle back, exactly like the threading API in the normal standard library. Gives you a join handle back that is in itself a future, and the operation that this future represents is wait for the background task and then take the result back. So these are two different kinds of operations. It's always important to understand what is the thing that I'm actually waiting for. In this case, first of all, I'm waiting for the file to be read. Second, I'm waiting for the background task to complete. Join handles, much like the join handles in the standard library, will give you the result back that the task result. Join handles are similar to standard join handles. They're allocated together with the task that they spawn in one go. This is a single allocation, and they also provide you a back channel to the spawner, and the join handle resolves for it. There's a second function, and I mixed up my slides. This should be spawn blocking up there. There's a second function called spawn blocking. The body is correct. This is the old standard lib API. So this does blocking I/O, opening a file. And the way the standard library works is it will block the current thread until the file is opened, until the kernel wakes up that thread again. But spawn blocking indicates to the runtime, by the way, I am aware that there's blocking tasks, there's blocking things in this task, which will make the runtime put the task on a single thread, on its own thread, to avoid blocking other concurrent tasks. It behaves exactly the same. It gives you a join handle back. So what's possible, for example, is having blocking and non-blocking tasks resulting in the same time of result, mixing them, for example, putting them all in a vector and waiting for all of them. So our model unifies these things on the level of the caller, or on the level of the spawn. There's two patterns on futures that I would like to introduce you to, which are important. The first one being racing, the second being joining. What does racing mean? Racing means I take two operations and I wait for the first to complete. As an example here, I use the surf HTTP client, and I'm trying to get the index of two mirrors, for example, and I want to check out which one answers fastest. What I can do then is I can say, take the first future, race with the second, await, and I will get the first result back, and the second will be dropped, and will be removed, and potentially the request aborted. So this is racing. Sometimes in the futures, RScrate, there's also a macro called select, which will have similar behavior, but not quite. But you may have seen that one. What's important here is, when we're talking about concurrency versus parallelism, these two are concurrent because I'm taking two of these, I'm putting them on a concurrent, I'm merging them into the same future, and then I'm running them both and on the same task. What I can also do is I can spawn both of them, which may run them in parallel because now the runtime is free to do so, and then race for the completion of the task. So this means I will, the spawner will say, let's join the join handles together and wait for one of them to return. So this is a similar kind of execution behavior, a different kind of execution behavior. The last pattern that I would like to present is joining. Joining is important in the sense of I have two operations and I want to execute them both, and I don't want to continue until they are both complete. So in this case, I want to make multiple requests to a backend and I want to wait until they are complete. The next concept I need to talk about is streams. Streams are a fundamental abstraction around items arriving concurrently into any kind of part of my program. In async-std, they take the place of the iterator trait. So basically, standard iter is replaced by async-std stream. So they can be split, merged, iterated over, all these kind of things. The classic example that you will probably have seen if you have ever had a look at async code is, and also even at sync network code, is the TCP listener. So the concurrent component of this is new connections are arriving to my program. I don't know when, I don't know how many, and I don't know how many at once. And streams give you the ability to work on this one by one. So the TCP listener on the standard lib has a sync incoming iterator. We have a sync incoming stream. And in now Rust 139, the recommended way of iterating over that is calling incoming next, stream.next. This is a future because we don't know if there's something there yet, or it might come in the future. So this will lay the task sleeping until something is coming in, and we're waiting for it, and we're matching on it using the while-let syntax. There's no integration into for loops currently in the language, so while-let sum is your pattern to use. And then we spawn, for each of those connections, we spawn a concurrent task that works on them. Process is some function that processes this. And one important operation on streams is merging them. There's a couple of other operations, but I could give a whole talk on over streams on streams. Here's an example that listens both on a IPv4 and an IPv6 interface. So I can use two TCP listeners, bind them, get the incoming stream for both, and then I say IPv4 merge to IPv6, and then just continue, because they are returning exactly the same things. They're giving me a TCP socket with a TCP connection, so I can merge them and then start iterating over them. We have a sync module, exactly like standard sync. Comes with async await ready versions of standard lib structures. It is important to understand that a lot of standard lib structures, if they put you waiting, like for example, you're trying to lock a mutex, they will lock the current thread. So what our port gives you is they will lay the current task waiting. So it comes with mutex, barrier, read-write locks, all that. The classic. This is what the code looks like. This looks almost exactly like the standard mutex example that you have. If you look at the middle line, the difference here is the .lock.await. So if I can't get access to the mutex currently, lay my task sleeping, let other concurrent tasks run, and wake me up when it's my go. So it is important to use future-aware data structures in future code. One interesting thing is we have the ARC here. This is just an export from the standard library to make sure that you don't have a mix of STD and async STD types. Almost all types that async STD exports are either exported because they have a relationship to another one, or because we need to make changes. ARC is the small exception, and we don't want people to be too confused by having these small exceptions of maybe 1%, 2% of the interface. That becomes. We have a channel implementation. Async STD channels are based on cross-beam channels, but in an async version. There are multiple producer, multiple consumer channels. They're always bounded. We think that unbounded channels are an anti-pattern. You will run into problems with unbounded channel at some point, and then you're switching to bounded channels anyways. What that means is they can only bounded channels can only hold a certain number of items at once. Otherwise, trying to write into them will lay your task sleeping. And they're very fast. They're faster than cross-beam channels. Cross-beam channels are the ones that are used in Servo in the browser end. Because they're multiple producer, multiple consumer channels, they should cover all your generic use cases. So that also means they cover one-to-one, they cover one-to-multiple, they cover multiple-to-one, just by virtue of covering end-to-end. Channels are currently unstable for API discussions. We want to fix that in the next couple of weeks, so you need to activate the unstable feature flag if you want to play around with them. Just as a short example, they work much like the stuff that I introduced. Specifically, the receiving end of a channel is a stream, so it can generically be seen as a stream. So the while let sum pattern applies. If you send, sending becomes a future operation, because if the channel is full, you will have to wait until the channel has capacity. And this is a ping-pong example of two tasks or two futures that will ping-pong each other through a channel or through two channels. And you spawn both of them, and they will stop playing ping-pong until kingdom come. Understanding tasks and streams, in my opinion, is far more important than understanding futures, because streams, channels, and tasks are the things. Tasks are the things that communicate. Streams and channels, streams being the abstract version of channels. Not everything, almost all channels are streams. Not every stream is a channel. Those are the things how tasks communicate. So this is, if you have the problem, how do I get some piece of data from A to B between two concurrent tasks? The answer is almost always use a channel. And so even if you're talking about, I want to work on a futures-based system, it is important that you have that in mind. So as a summary, async-std provides a known and familiar interface, the known and familiar interface of the Rust standard library with appropriate changes for async. It avoids pitfalls by providing a full API surface around all async critical modules. It is fully based on Futures RS, so it integrates into the ecosystem very well. We fully embrace the Futures RS library. So if you want to use async-std in an abstract fashion without relying on async-std types, you can take a step up and rely on the Futures RS interface traits, because all types expose the relevant interfaces from Futures RS. So futures, obviously futures, but async-std streams are always also futures streams, and everything that is read-write, async read-write is also futures async read-write. If you want to have the full interface of Futures RS, then you can also, on top of that, load the Futures RS library. One note about the Futures RS library: it has recently been re-architected to a core and a util and a couple of additions. And from core to util to some of the more remote additions, it becomes more and more experimental. So when I say we export the Futures RS library, specifically we rely on the core types where we know that they're going to be stable and probably not subject to churn. But if you want to opt into any of the more experimental types, you can totally do so by just loading the Futures RS library on top and using it. Particularly of interest are the async read, async write, async seek traits. A lot of the criticism that we got is you're not compatible with the ecosystem, particularly Tokyo. The problem there is a lot of libraries are written on top of Tokyo, which don't implement the Futures async read, write, seek traits unless you use a compatibility interface. They use Tokyo IO async read, write, seek, which are different and also subject to change, making them incompatible with the rest of the ecosystem. I think it's okay. Their view on this is we still want to experiment on this, and we would like to iterate on that interface, but that very much collides with our view that we should get stuff stabilized and that we have researched those traits for 3 years. So addressing the common question, why async-std, it's pretty simple, fundamental mission goal. That's as deep. Our view and vision for using std is applications should use async-std directly, because application development is far less abstract. You want to pick a couple of libraries solving your needs, use them, and then in the abstraction level is usually pretty low. You want to get stuff done. Libraries should use futures or S as their interface. As an example, we have a TLS library under our own organization, async-rs/async-tls, and this one operates completely on top of async read, async write. So it has no direct relationship to async-std, except that you can use it on all async-std, TCP socket, and so on, so forth types that expose read and write. So to make this more concrete, if you're in an application, it is okay to take an async-std net TCP socket directly. If you are in a library, I would highly recommend you to instead use futures IO async read. So that doesn't expose users to your choice of base runtime. Because there are other runtimes around, and this is something, there's currently a binary discussion happening around async-std versus Tokyo. I don't want to have this discussion because there's a number of additional executors in our ecosystem. Particularly Google Fuchsia is a very big one for the Fuchsia ecosystem. There's Bastion RS, which has a very different goal than async-std, which is this thing never crashes under no conditions. There's Wasm BindGen Futures, which is a particularly built executor for Wasm. And there's a number of company internal ones that those companies sometimes speak about, but pretty rarely speak about in public. And async-std is meant for writing compatible libraries. So if you're writing a library, you can use async-std as your test bed. Probably you should avoid binding to it direct. Which brings me to speed. That has been something we've been asked about a lot. There's a problem there. We also believe that there's a hyper-focus on benchmark in the Rust community at the cost of ergonomics and barring stabilization. The biggest problem with benchmarks is they're often changing. We don't really want to be part of the benchmark race. So probably I'll present these benchmarks, and in 2 weeks they will look very, very different. And I also don't believe that you should choose software by benchmarks alone, which doesn't mean they don't factor into play. Still, on file reading, async-std is 1.6 times faster than Tokyo. That was done by Jay Brosen. You can have a look at that benchmark repository. So that's only on reading a 256K file. If your application has a different read-write behavior, your benchmarks might be different. That's a fair warning. Our mutexes are fast. There's a fastest at creation, up to 9 times faster than the ones from Futures Lock Mutex. There's multiple interesting mutex implementations. There's also a very nice crate called Futures Intrusive, which also gives you a lot of the base types that we export. So we are roughly twice as fast as Futures Intrusive and 9 times as fast as the Futures implementation at that. This also gives an interesting insight of, should I use Futures Lock Mutex? These types are mostly implemented for making sure that people can use them and run with them. So these were for the experimentation phase of Futures, and they're still shipped so that people that are rely on them can still use them. They are good. They are just not built towards they should be fast. So this is mutexes under contention. So actually mutexes where there's frequent locking. There, we're up to 2 times faster than the fastest one, and we're the fastest one under contention. Mutexes without contention, and that is interesting, also have a speed fast. So mutexes that are rarely actually challenged. And there we're around roughly the same speed. Why do I say the same speed? When we run those benchmarks, they're highly variant. In the sense, the results will remain clear. Like the implementations don't change spot, but on the other hand, some of those numbers change up and down. And finally, how fast is task spawning? These are the Tokyo 10 times benchmarks. We're as fast and up to 2 times fast. There's another benchmark where we're slower, which is the channel ring benchmark, which is the classic Erlang benchmark that tests single-threaded executors, where you put up a number of nodes and connect them in a ring, and then you send a message around as fast as possible, multiple times. And there we're 0.9 times slower than Tokyo and roughly 3 times faster than Hack. So, yeah, notice, for the risk of side effects of synthetic benchmarks, please consult your local Apple keynoter. Conclusion, async-std is a fast ergonomic future-based layer for asynchronous applications. It is an innovative space. I want to mention that again. Join handles were built in async-std and then adopted by others. Single allocation tasks were invented or implemented first in async-std and adopted by others. You can both innovate and commit to stability. Be aware what which strategy you use. Our roadmap is our 1.0 will be released on Monday, so tomorrow, which will be a stable release with all base functionality and runtime concerns. Ongoing is stabilization of currently unstable library API, most importantly, channels. Also, designing features that make async-std usable without the runtime. I think this is particularly interesting. What if I want all those features, but I actually don't want the runtime? We want to provide additional libraries with similar guarantees, ecosystem compatibility, 1.0ness, interface stability. And just to be clear, there's a clear bet that we're going to have a 2.0 at some point. Because there's new language features arriving, and some of those might lead to breaking interface changes, not only in base grades, but for example, there is an asynchronous for loop coming, and that might need some interface changes to integrate well with that. And when these changes are coming down the line, we will release a 2.0 plus update guides on how to do that appropriately. And we would like you to hack with us in the next few days. So getting started writing more libraries on top or porting libraries to work with multiple executors. We want you to challenge our benchmarks because all benchmarks are wrong. And let's figure out how. If you want, we can get started writing an application, and we would like to get a lot of feedback on our unstable API because we want to stabilize, and that means we need a couple of eyeballs. Finally, async-std is currently completely funded by Paris Systems, and we have started offsetting for all those projects. We are also hosting, for example, Rust Analyzer, an open collective. So if you agree with all those goals and would like to give us some more time to work on it, here's a funding drive. Thank you.
Thank you, Florian. We have time for 2 questions. Hands, please.
Hello, thank you for the talk. It was a great talk. Do you think there are ever any use cases in which Tokyo should be preferred to async standard?
Sure. No, seriously. There's at least 6 executors that I know of around. All of them with different tuning settings, different kinds of APIs. Yes, there's reasons for all of them. Tokyo currently has a better API for fine-grained control of placing of a runtime, which is a very, very detailed thing to do and needs a lot of knowledge on how to actually place runtimes correctly. And this is something that we currently don't provide at all. So, yes, definitely.
You mentioned that racing and selecting aren't quite the same thing. Could you elaborate on that?
So the select macro of the futures crate is a pretty big beast that works on top of a library called proc macro hack, which implements by itself a way of doing, basically implements its own match statement along with 2 different kinds of operations to how to react to an event happening on each of the sites, on each of the branches. So, yeah, so what I was hinting at is this select in Rust isn't a very well-defined term, while racing is pretty clearly there's two futures giving you the same results. And that's also the other thing. The select macro in the futures crate allows you to use two futures that return different kinds of results and react differently on whether the one resolves or the other one resolves. While racing is, I expect the same back and I wait for the first. So it's a vastly simpler operation.
Thank you, Florian.